Hello guys, welcome back, and today we're going to talk about quantities. So there are basically two types of quantities. One of them is vector quantities and the other is scalar quantities. So let's start with scalar quantities. Scalar quantities are the quantities which only have magnitude. Now what is magnitude? To explain this, I'm going to write down three quantities measurements. First one is going to be length, for example 3 centimeter. Next is going to be mass, like for example 15 kg, and then I'm going to write a temperature such as 30 degrees Celsius. Now you see, one thing common in between all of these measurements is the magnitude. The magnitude is the numerical part of any measurement. So for the length we've got 3 centimeter as the magnitude, for the mass we've got 15, and for the temperature we've got 30. This is magnitude. Scalar quantities are the quantities which only have magnitude, which is why, for example, we've got speed, distance, time, temperature, mass and energy as scalar quantities, because they only have magnitude. Now if we talk about vector quantities, these are the quantities which have magnitude and direction. Now what does direction add to? So you see, direction tells us, indicates that which direction this quantity is acting upon. For example, force, we can say that there is a force of 3 newtons, but we also tell that this 3 Newton force is acting in, for example, north direction. Or if we talk about displacement, we can say that an object is displaced 15 centimeters, but we also tell that this object has been displaced towards the east or west or any other side. This direction makes this quantity vector. So for vector quantities we've got force, weight, displacement, velocity, acceleration, momentum, electric field and gravitational fields. All of these quantities have a magnitude and direction. Okay, so to further explain this concept, I've got an example. So let's say we've got a point A and a point B. I've made two paths. One of them is a curved path which is shown by the red line, and the other is a straight path shown by the orange line. So as we can see that the curved path has the length of 17 centimeter, and we call this distance. Why? Because it is not in a fixed direction. First, as you can see, it's going upward, then towards B, then it's going downwards, then it's going towards B again, then upwards. So it doesn't have a fixed direction, thus it is a scalar quantity, distance. However, if we talk about the orange path, we can see that it goes directly from A to B. So we can see that this is the displacement, and it has the magnitude of 5 centimeters. So whenever we write displacement, we're going to write, for example, in this case 5 centimeters A to B. In this displacement we've got 5 as the magnitude and A to B, or towards B, as the direction. Okay, so another example that we can talk about is the difference between speed and velocity. So let us imagine that we have a car here. This is our car. This is point A and this is point B. Now our car is going to move towards point B with a speed of 15 meters per second. Okay, now in the next scenario, our car is going to reach point B, and then it's going to come back towards A with a speed of 5 meters per second. Now you see, if we're talking about speed, speed is positive in both cases. For the first case it was 15 meters per second, and in the second case it became 5 meters per second. However, if we talk about velocity, we can say that the velocity is positive 15 meters per second towards B, but when we talk about the second case, we can see that the object is moving towards A, which is opposite towards the direction of B. This means that the object is moving in the opposite direction to its original velocity. So for the first case, if it was moving towards B and it had a positive velocity of 15 meters per second, now it's going in the complete opposite direction and has a speed of 5 meters per second. So we can say that it's going at a velocity of minus 5 meters per second towards B. So let me explain this a bit better. So you see, we're talking about the velocity in the sense that an object is moving towards B. Now in this case, the object is moving away from B, so we can't say that it's moving towards B. If moving towards B was positive, going opposite to that is going to be negative. Another small example for this is, for example, this ball. We can say that when this ball moves upwards, it has got a positive displacement of, for example, plus x. However, when it reaches towards point B, it comes to a stop and then it wants to move back to its original position, so it's obviously going to come back down. Now if the positive upward displacement was positive, as we can see, then the downward displacement, which is directly opposite to that, is going to be negative. I hope that made sense. Okay, so now we're going to be talking about the addition of vectors by implementing the concept that we learned earlier. So vectors are the visual representation of vector quantities. So for example, vectors are represented through straight lines in a particular direction. For example, as we can see here, we've got a bigger line of 5 newtons and a small line of 2 newtons. Now this line, as we can see, is smaller because it has a smaller magnitude of 2 newtons, while this line is longer because it has a larger magnitude. The vector lines also represents their direction. So if we're talking about these two arrows, they have an overall direction in this. Okay, so now we need to learn how to add vectors. So for our syllabus, we have 2 ways that we can use to add vectors, and we will talk about both of them one by one. The first one is by rearranging the vectors. So as we can see here in this example, you've got 2 vectors, one of 3 newtons and the other of 6 newtons. Both of them have an angle of 90 degrees between them. So the first step is going to be rearranging of vectors so the head meets the tail. Okay, so let's zoom in. In this example, we can see that this is the head of the 3 Newton force and this is the head of the 6 Newton force. This is the tail of the 3 Newton force and this is the tail of the 6 Newton force. But the heads are not meeting the tails. So we need to arrange these vectors somehow that one of the head meets one of the tails. So what we do is that we take this 6 Newton vector and we move it upwards. So as you can see in this part of the example, we have moved the 6 Newton vector upwards so that its tail meets the head of the 3 Newton force. Now what we do is that we connect the last head with the last tail to form a triangle. This hypotenuse that we join with the head and tail is going to be a resulting vector. So it will have a magnitude of x, and we'll calculate this magnitude using the Pythagoras theorem. So as we can see, this is a right angle triangle. We've got the base and we've got the length. So let's just calculate the hypotenuse using the Pythagoras theorem. X square is equals to 3 square plus 6 square. Then we're going to add both of these and we're going to solve for x basically. Okay, so now let's try to do this example on our own. So we've got 2 vectors, one of 4 Newton and the other of 3 Newton, and they've got an angle of 90 degrees between them. We can see that the heads of both these vectors are not meeting, they're in the opposite direction. So now what we want is that we want one of these heads to meet one of the tails. So what I'm going to do is that I'm going to move the 3 Newton force vector upwards so that its tail meets the head of the 4 Newton force. So I'm going to take this and I'm going to move it upwards, and now we can see that the tail of the 3 Newton vector is meeting the head of the 4 Newton vector. Now what we want to do is now we want to complete this triangle by meeting the head and the tail that's left. So I'm going to take a different color and I'm going to draw a line like this. This line that we see is our resultant vector. We don't know this resultant vector, so I'm just going to call it x. Okay, so now we're going to solve for this resultant vector using the Pythagoras theorem. we've got 4 and we've got 3 as the base and the height, and now we just want to find out the hypotenuse. So x square is equals to 4 square plus 3 square, x square is equals to 16 plus 9, x square is equals to 25, and now we're going to take under root on both sides to solve for x, and we'll have 5 Newton as our resultant vector. Okay, so another thing I want to talk about is how we can logically solve this question. So we can see that our resultant vector is going to be in this direction. The tail of the resultant vector is going to meet one of the tails, and the head of the resultant vector is going to meet one of the heads. So in this case, the resultant vector tail is meeting the tail of the 4 Newton vector, and the head of the resultant vector is meeting the head of the 3 Newton vector. So another very common sense that we can use to solve this question is that we've got a force which is going upwards, and we've got a force moving towards the right. Now if we imagine an object, and if we imagine these forces on that object, it is very obvious that the object can't go downwards because it has an upwards force. It can't go towards the left because it has a force towards the right. So it is very obviously going to go in the middle of these two forces. As you can see, our resultant vector up there is also going in the same direction. The next method is going to be the graphical method. It is very possible that it comes in your exam, and this method can be a little tricky because you have to make sure that your measurements with your scale are very accurate. So the first thing that you want to do for this type of question is choose a suitable scale. For example, you're going to say that I am going to represent 1 Newton of force with 1 centimeter. Then you're going to draw the vectors using the same scale. So for example, in the question, if they've given you two vectors, one of 3 Newton and one of 6 Newton, and you've got the scale 1 Newton is equals to 1 centimeter, you're going to represent 1 Newton of force with 1 centimeter. So you're going to make a vector of 3 centimeters here, and then this vector is going to be of 6 centimeters. Next, what you want to do is complete the vector diagram. You want to complete this vector diagram by, for example, in this scenario, completing this rectangle. You're going to draw those two imaginary lines which are going to be equal to the vectors that you've already drawn. So for example, this is going to be 6 centimeters and this is going to be 3 centimeters. Make sure the angles between the two vectors are also the same. The final thing that you want to do is use a ruler to measure the length of the diagonal and that will be your resultant vector. So you're going to make a diagonal between this rectangle, and this diagonal is going to be your resultant vector. You can use a scale to measure this diagonal. So for example, if in this scenario, I'm not saying that this is accurate, so in this scenario, if you measure it using a scale and it comes out to be, for example, 8 centimeters, so using your scale, you know that 1 Newton is equals to 1 centimeter. So if I've got 8 centimeters, this will most probably be 8 Newtons. Okay, so now we're going to do another example for the graphical method of addition of vectors. So in this question, we've got two vectors. One of them is 10 Newtons and the other is 6 Newtons. Now the first step that we're going to do is make a scale. So what I'm going to do is I'm going to make a scale of 2 Newtons is equals to 1 centimeter. Now what this means is that we're going to represent 2 Newton of force with 1 centimeter. The first vector is 6 Newton, so our length for this vector is going to be 3 centimeters. Now our other vector is 10 Newton, so the other vector is going to be 5 centimeters. Now I want to say that I haven't made this with scale, so I'm just giving you guys an example. You guys have to make it with your own ruler in exam. Another thing that you're going to do is you're going to measure the angle between these two vectors. So in this case, let's say it's going to be 120 degrees. Okay, so let's move on to step 2. Now we've got half of our parallelogram complete. The second step is to complete this vector diagram. So one of our vectors is 3 centimeters, so we're going to make the exact copy of this vector on the other side. So we're going to make a line of 3 centimeters here, and to make it accurately we'll need to measure this angle here, which is going to be 60, and ensure that this angle is also 60. Next we're going to copy the 5 centimeter vectors and join it with the 3 centimeter one. This is also going to be, this is going to be 5 centimeters, and to check if you've got it right is by checking the angle between the 5 centimeter and the 3 centimeter vector here, and ensure that it is 120 degrees, because it should be identical to your own original vectors. The last step is to make a diagonal. So we're going to make a diagonal, and this diagonal is going to be our resultant force. Now what we can do is, after making this diagonal, you can use your ruler to measure the length of this diagonal, and then we're going to use that to calculate the magnitude of our resultant vector. So for example, I'm just giving an example here. If this in our scenario comes out to be 8 centimeters, we know that the resultant vector is 8 centimeters. Now we're going to use the scale to convert this 8 centimeters into newtons. So if 1 centimeter is equals to 2 newtons, we know that 8 centimeters will be equal to 16 newtons. With this we get the magnitude of our resultant vector, and we solve this question. I hope that you guys found this video interesting and helpful. If you have any questions, don't forget to leave them down below in the comment section, and I'll try to upload a video of me solving past paper questions for this chapter.